All right, and now it's time to revisit some of our applications with exponentials and logarithms. And we've talked about some of them, right? We've talked about growth and decay being, this constant b to the t or e to the rt, and we can just represent b as e to the r. For instance, we've talked about loudness, magnitude of earthquake, and pH of a substance for logarithms. And so now we're going to focus primarily on this equation up here. And I am going to most likely always use the format P of t and is equal to P naught e to the RT, just because the right side you can say it's PERT. But really P here, we're mostly talking about a population, but you can certainly use A of t for an amount of a population too. If there's no notation provided, use whatever you like, but use proper notation. All right, so just to recap here, P of t here, this would mean, your amount or population at time t. P naught would be your initial amount or population, initial amount or population. E is your exponential number, so approximately 2.71. You could find E on your calculator. It should be a second feature right above natural log, approximately 2.71. And then R is your rate constant. Most of the time we're going to have to find this, and then T is just whatever. It's a variable, but it's going to be time, okay? So this application, this P naught e to the RT, comes by way of exponential growth and decay frequently. And so here, we're looking at a situation where we're studying the population of Texas. And so it's approximately 21 million people. And then on January 1st of 2000, and then it says later, 10 years later, the population increased to 25.2 million. And so we want to write the exponential function that represents the population in Texas in millions of people, t, and then t years after 2000, and then it says round k, or really k should be r here, rounded to 5 decimal places. All right, so what I'm going to do is begin with my basic model. P of t is equal to P sub 0 e to the RT, and here P naught would be the population of Texas at our starting time, which would be year 2000. So in this case, it would be 21 million, but again, it says population in millions. So I'm going to call that population of Texas in millions of people. I'm going to define that as P of t. Okay, so we have 21e to the RT is equal to P of t. And when we talk about writing a function to model this, I also need to figure out what R is. And that's where I might be stumped a little bit. But I have to recognize there's some information I haven't used. This 10 years later. So when t is 10, P of t is equal to 25.2. Oh, okay, so let's substitute that in to our equation. So I'd have 25.2 is equal to 21 e to the r times 10. Okay, so I need to get at this r, so I'm going to need a logarithm. Divide by 21, so I'd have 25.2 over 21 is equal to e to the 10r. Okay, I'm purposely not dividing this. If you divide this, you're going to have a tendency to want to round. You're going to, when you round, you lose accuracy. Do not round until the very end of the problem. Okay, so now this is an exponential equation. Change it to logarithmic form. So I'd have log base e, also known as natural log. So I'd have natural log of 25.2 over 21 is equal to 10r, the exponent. So then divide by 10, and I'd say r is equal to 1/10 times the natural log of 25.2 over 21. Okay, and so now we can put that into our calculator, because at this point I can't go any further and I have r completely isolated. Okay, so if we punch this into our calculator, we end up getting r is approximately, and it says round to 5 decimals, so 0.01, that's 2 decimals, 823. Okay, so then my final model, my answer here is going to be P of t is equal to 21 e to the 0.01823, 5 decimal places, and then times t. My final answer needs to be in terms of t because I have a function of t, function of time, all right? And that's what my answer is going to look like, all right? So, part B, it says use the function above to predict the population of Texas in 2022. So this would be P of a number. So I have to, wait, 2022. Oh, yeah. Okay, so that's time, right? Time in years after 2000. Okay, so that would be 22 years after year 2000 is equal to 21 e to the, okay, 0.01823 times 22. Okay, now when you put this into your calculator, make sure that exponent's completely in parentheses. And when you do, you get, this is approximately 31.3, oh gosh, I don't even, how do I round this? Let's do just one decimal place, 31.4 million people, okay? Really, we should write this in a sentence, but I'm going to let you imagine what that sentence would look like for time purposes, okay? But if we're in a context, you should always report your answer in context form. All right, so that was part B. Part C says, use the function to determine the year during which the population will reach 40 million. Okay, so I'm saying P of t is equal to 40. And I know P of t is also equal to that, so this is equal to 21 e to the 0.01823, and I don't know the time value, but I'm trying to find that. Okay, so we have an exponential equation to solve. Isolate the exponential. Okay, so 40 divided by 21, divide that over first, is equal to e to the 0.01823. T, exponential's isolated, so switch it to log form. Natural log 40 over 21 is equal to 0.01823 t. Okay, divide that 0.01 number over natural log of 40 over 21, all divided by 0.01823. And now we have to calculate. And if I do, I get t is approximately 35.3. Again, I'm rounding, but it's now the answer that I'm reporting, it's asking about the year, right? So this is 35.3 years after 2020, or 2000, sorry, after 2000. So then I'm going to say, okay, it's going to be in 2036, because it would be 35 complete years, and then it would be during year 2036. The population will reach 40 million. Okay, so there we go. So that was a situation where we're growing, where it's increasing. The amount is increasing steadily over time. Now, in other cases, we talked about carbon-14 and various other examples in the course, and so that one, the amount is decreasing over time. It's decaying, and so we know it's radioactive, and it talks about half-life being that, and so we want to determine the age of a bone where we have 42% of its carbon-14 remaining. Okay, all right, so there's a lot to do here, but again, we can start at the same place. We have P naught e to the RT on the right side, and this would just be equal to P of t, okay? Here, let's actually change it to the amount, okay? A of t, for amount, okay? I should go through and define, like, A of t is the amount of carbon-14 at time t. Since there's no symbols defined, I should really go through and define that, but alas, here we are. So then, I don't know what A naught is. I don't know what R is. I actually don't need to know what A naught is. But what I do know is that the half-life is this. So this is saying when T is 5730, the amount is half, oops, the amount is half of the original. Oh, okay, so let's put that in. I have a naught over 2, the initial amount divided in half, is equal to a naught e to the r, and then times 5730. Oh, okay, so then now I can divide the a naughts out, and again, 1/2 is equal to e to the 5730r, and this is just like the previous one, so switch it to log form. Natural log 1/2 is equal to 5730r. Okay, divide by 5730, and that's r. So 1 over 5730 times natural log 1/2 is equal to r. Okay, so then my model is a of t is equal to a naught e, and then r is now 1 over 5730 times natural log of 1/2 times t. Okay, and then now it says determine the age time that is 42% of its carbon-14 remaining. So the a of t would be 42% of the initial amount. So this would be a naught, and then all the rest would stay the same. I'd be looking for t. 1 over 5730, natural log 1/2, all times t. Divide the a naughts out, I'd get 0.42 is equal to e to the 1 over 5730, oops, 5730, natural log 1/2, all times t. Convert to logarithmic form. Man, this is a lot of work, but it's a good problem. It's good practice in using your logarithms. So convert to a logarithm, so I'd have natural log of 0.42 is equal to 1 over 5730 times natural log 1/2, all times t. And then to isolate t, all this other stuff in front of it needs to move over. So I'd have, at the end of the day, 5730 times natural log of 0.42 divided by natural log of 1/2 is equal to t. That was a lot of algebra that was presented very quick. If you have questions, let me know in class. And finally, to get our answer, we need to get this in our calculator. And when we do, we get about 7171 point, and it says round to the nearest 10 years. Oh, okay. Okay, so then rounding to the nearest 10 spot, so I need to round at this place. T would be approximately 7,170 years. So I would say the bone is about 7,170 years old. Okay, so that is the answer. And I just want to clarify too, notice how throughout I did not round at all. Okay, really the rounding should only occur at the very end of your answer. Once you're ready to report your answer, that's the only time you round. So even though you might be tempted to get a number for r that's 1 over 50, you put this in your calculator, 1 over 5730 times natural log 1/2, I encourage you not to. Don't round unless you're directed to, okay? And the only place that we were directed to round was at the very end. Annoying to write out, I know, but it'll really help with the accuracy in your answers, all right? So, point of all this is, word problems, fun, a lot of work, but really, once you get through the context, you're effectively just solving an exponential or logarithmic equation, and we know how to do that. Try and isolate the exponential or log, switch it to the other form, and go. All right, so that is the last video you're going to watch in this course. Congratulations, you made it through Pre-Calc 1.